And today we are covering Chapter 4 in the normal distribution. So last week we left off with Chapter 3, which covered probability and the binomial distribution. Okay, so last week, Chapter 3, which was probability rules, and the binomial random variable. Okay, and so this week we'll cover Chapter 4, which will do the normal distribution. And then we will also look at one section in Chapter 5, which covers the normal approximation to the binomial. Okay. Oh, and then also a little bit of R for the lab. Okay. So again, if you think back just to the beginning of our course, let me enter this, stats 13, April. Let me just see if I can find this. Okay, so first day of class, I said we learned about the basics of data description and data collection, and then we're still today we're still in this section on probability distributions. Okay, so last week we learned about probability in Chapter 3, and we learned the binomial distribution, and today we are still learning more probability distributions on and it's the normal distribution, which is a very important one. Okay, so that's where we are. Okay, and the normal distribution is a random variable or the normal random variable is random variable, and it's continuous. Okay. So that's in contrast to the binomial random variable, which was discrete. The binomial random variable, the values it could take on were just whole number things. We would say we're going to take a random sample of 20 seashells, and we want to know what's the probability that 12 are streaked or 14 are streaked. Okay, so the random variable could only take on whole numbers, 11, 12, 13, 14, something like that. Okay, the normal distribution is continuous, so it can take on any value to any degree of with some infinite number of decimals. Okay, so you could have y could be equal to 71.02. It could be equal to 71.023641, and these are all possible values from the normal distribution. So it's continuous. There's no restriction in terms of the values it can take. So technically, the normal distribution, results of the normal distribution could be anywhere from negative infinity to positive infinity. Okay, so a true normal distribution goes from negative infinity to positive infinity. Okay. And a lot of things in real life are approximately normal, okay? So the heights of people are approximately normal. It's not going to be truly normal because nobody can be negative infinity inches or centimeters tall, and nobody's going to be positive infinity, okay? But in a true normal distribution, the probability of being at negative infinity or positive infinity is infinitely small. It's, you know, non-zero but infinitely small. And so when we talk about the distribution of human height, it's approximately normal. Okay, and so the normal distribution is very useful because a lot of things in real life follow or can be approximated with the normal distribution. Many data distributions in real life. Okay, so the normal distribution looks like is what is known as the bell curve. Okay, it's unimodal and symmetric. Sometimes called because I guess if you put a handle on it, it looks kind of like a bell. and the idea being that values in the middle are most common, and as you go further above the middle, these values become less and less common. And if you go in the opposite direction, below the middle, they also become less common. Okay, so things that are approximately examples of approximately normal distributions from real life. So height values are approximately normal. IQ, so intelligence scores. Be it IQ and even to a degree SAT scores are approximately normal. Values in the middle are most common. Values high above the middle, slightly above the middle are also common, but as you go further and further above the middle, they become less and less common, and going in the opposite direction, the same is true. Yes?
With like intelligence test type example, do you have any idea of that, how much of that's due to designing the test to produce that sort of distribution?
Yeah, so the tests are designed to produce a normal distribution, but yeah, I guess it's a chicken and egg problem, which goes which way. So the questions are selected in a certain way, or I guess the scoring system is set up to produce this normal distribution, and the questions are selected in a certain way as well. That was actually related to my dissertation. I didn't do specifically IQ or SAT work, but similar field, I guess. So those are normal distributions. The book does a few different examples, but we can just make one up. Okay. So actually, let's see. Let me pull this up here. Not that one. So here we're looking at serum cholesterol levels, okay? So this is from our textbook. This is the older edition, but we looked at 727 12 to 14-year-old children, and we measured basically their cholesterol levels in their blood, okay? And it's measured in milligrams per deciliter. And this is the histogram, okay? The histogram looks like this, and they are trying to approximate this histogram using the blue curved line, which says this is a normal distribution, okay? So it's not a perfect fit, but it's not terrible either, okay? It's fairly good approximation, meaning that cholesterol levels around 150, 160, these are quite common. And cholesterol levels that are much higher than that, 220, 240-ish, these are less common, but they exist. And if you go in about that much in the opposite direction, down to 100 or 90, whatever it is, they're also less common. And everything in between is somewhere in between as well. Okay, so we're looking at an actual data distribution, and we're trying to approximate it with a normal distribution, like so. Okay, and so all normal distributions are defined by two parameters, a mean and a standard deviation. Okay, so let me put that in our next slide. A mean, and the symbol for the mean is mu. Looks like a U with a tail in the front, and a standard deviation. And the symbol we use for that is sigma. We're using the Greek letters here, not Y bar and not S, because here we are talking about the theoretical distribution. We use S for a standard deviation and Y bar for the mean when we're talking about summary statistics for a sample of data. Okay? But here we're talking about a theoretical distribution, so we use the Greek letters. Okay?
How is that a sigma?
This?
Yeah.
I don't know. That's what does a sigma look like? This is what sigma looks like. So, huh?
It's lowercase sigma.
It's a lowercase sigma. Yeah. So it's technically from, you know, our letter S is technically from kind of this somewhat related, but I don't know. I guess if you look at the history of writing and stuff, the Latin alphabet and the Greek alphabet, some parts are related, but you know they're also different. So anyway, Greek letters for their populations and theoretical distributions. Okay, so actually, let me, I want to copy this. No, that's not what I wanted. Go back. Oh gosh, how do I undo this? Come back. Here we are. Yes. Let's shrink that a little bit. Put that right there. Okay, so here we see this is actual data. actual data with the histogram. Okay, we approximate that. So we're approximating it with the normal distribution. And here we've defined, we are using mu equal to 162 and standard deviation equal to 28. That's what this means. Okay, so all normal distributions have a mean and a standard deviation. Okay, so let's go into a little bit of what exactly that entails. All right, so I want to copy this. I'll make a new slide. Let's blow this up. And actually, let's cut this. All right, so we previously said the mean here is 162, and the standard deviation is 28. Okay, so we have this nice little picture here, and so right in the middle, we put 162. Mu goes right in the middle, so in the middle, we put the mean 162. 162 plus 28 is equal to 190. Right? And so we end up out here. So this is one standard deviation above, and then if I do 162 minus 28, I end up at 134. Okay. So technically, as you know, when in the beginning, when you draw normal curves, you're not going to be very good, and I'm still not very good, okay? And so in the middle you put mu, and then if you go up one standard deviation, so let me, so this distance from here to here is one standard deviation, okay? And the distance from here to here, also one standard deviation. And technically, the spot where you go up one standard deviation is what they call the inflection point, or it goes from kind of convex to concave curve. I don't know if you guys are familiar with that, but where it changes a little bit in the hill, it's like I don't know how to explain without going into calculus and the second derivative changing from positive to negative. Where that changes, that's where the first standard deviation ends up being, okay? And then if I go up, if I do 190 plus 28, so 190 plus 28, that takes me to 218. So this, again, is one more standard deviation from here to here. And 134 minus, 28, another standard deviation, another sigma, takes me to 106, and that's how we end up with all of these tick marks in this graph here. Is that okay? And so, where's my brush palette here? Just pick a color here, okay? And if I shade in between from here to here, okay, so if I shade from one standard deviation below to one standard deviation above, so I shade, so if I shade from one standard deviation below the mean to 1 standard deviation above the mean. Okay. I have shaded approximately 68% of the total area under the curve. Okay, so if the total area under the curve is 1 or 100%, this area in lime green would be approximately, or whatever color this is, would be approximately 68%. Now remember, this curve represents the underlying data. Okay, so if I just flip back a page, okay, we're saying if I go approximately from 134 to 190, and I don't know where that is on this thing, but if I go approximately from 134 to 190, if this is what the picture looks like or something, I don't know if I'm doing this correctly. And if I shade in, everybody in the data, okay, the normal distribution says I would have shaded approximately, or approximately 68% of the people in our data set would have cholesterol levels between 134 and 190. Okay, of course it's not going to be exactly that, because this is just an approximation to the actual data that we have. But a lot of times you will hear statements such as approximately 68% of the data is within 1 standard deviation of the mean. And so in the relation to the serum cholesterol levels, the cholesterol data, we're going to say approximately 68% of the children we measured have cholesterol levels between 134 and 190. Okay. Are all of these statements okay? All right, and so there's kind of like this empirical rule. So the empirical rule states that, let's see, how can I write this? Empirical rule, okay, approximately 68% are within 1 standard deviation of the mean. Okay, so the mean is at 162. If I add 28 and I subtract 28, that takes me to 134 and 190, and we're saying approximately 68% are within that range. The empirical rule goes to the next step. It says approximately 95% are within 2 standard deviations of the mean. So if I were to shade in out here to here, we're saying everything in between 106 to 218, now that covers about 95%, okay, about 95%. And then almost everyone, almost all, and the true number is 99.7%, but of course this is an approximation, so it's not necessarily the case, but almost all are within 3 standard deviations of the mean. Okay, so if I pick one more color here, and I fill this in, and so this I go out 3 standard deviations to 78 to 246, that covers almost everybody. Are there people who might have cholesterol levels higher than 246? Yes, it's possible. Are there people who might have cholesterol levels lower than 78? Yes, it's possible. But according to the normal distribution, there should be very, very few people out in those ranges, because almost everyone, 99.7, so you know, less than about 3 in 1,000 will be outside of that range. But in general, by and large, the most will be within this. Okay. Is that okay? Normal distribution here. Okay. And so the neat thing about the normal distribution is that they all have the same shape. And each normal distribution is distinguished from one from another by different values of the mean and different values of the standard deviation. Okay? So if we change the sigma to something else, we would have another normal distribution, but it would all have the same shape. Okay? And all we would have to do is we would just scratch out these numbers. So if I picked, you know, let's just say I picked mu is equal to 100 and standard deviation is equal to 10, then all of this empirical rule stuff all holds true, except the numbers are now 100, 110, 120, 130, and over here 90, 80, 70, something like that. Okay? So it's the exact same shape. All normal distributions will have the same shape. It's just they're defined by having different means and different standard deviations. You change those. All of these things hold true. And so we can do this. Okay, so let's go on to the next slide. And let's just check our understanding here. Let me use this again. Draw another thing here. And let's, I'm going to just leave the same tick marks. I kind of like that. All right, so I'm going to just, oops. Okay, so let's say for adult females in the US, okay, height is approximately normal. Okay, and the mean average female height in the United States is around 5'4", 5'5". We'll just split the difference and we'll say 64.5 inches. Okay, so that's 5 foot 4.5 inches. And the standard deviation, just to keep things simple, we're going to just use this nice number 3. Okay, it's a little different from that, and so as we go further out, maybe the implications are a little different. But just to keep our calculations simple, we're going to just say 3. Okay? All right. So if I asked, so if we draw our picture, 64.5 goes right in the middle. And what would go right up here? 67.5, and down here I would have what? 61.5. Okay? So I'm just going to ask a simple question. Approximately, what percentage of women in the US have heights lower than 61.5 inches? Okay, don't shout out your answer, but think about this. Okay. And we're gonna, do you have a number in mind? Okay, and I'm gonna say approximately 16%. Okay, now how did I get that? Well, we said approximately how much is filled in here? 68%, right? So we have, if 68% is in here, okay, how much is not shaded? 32%, right? Everything adds up to 100%. So not shaded, so 68% between 61.5 and 67.5. That means 32% outside, right? Outside that range. Okay, and that 32% is split between the area above 67.5 and the area below. And the normal distribution is symmetric, so we would expect about 16% over here and 16% there. Okay, and so that's how I'm getting approximately 16%. Okay. Is everyone okay with that, or is there any questions? Okay, so then just oops. So it's much nicer to have the one that's pre-drawn, but let's if I go down, if I go 2 standard deviations above to 70.5, approximately how much would be out here? So what percentage is taller than 70.5 inches? And we would say about 2.5%, right? Okay, because we said about 95% are between, within 2 standard deviations, so we would expect 5% to be beyond 2 standard deviations from the mean. And again, that is split between the two ends, and so half of 5% would be 2.5%. Are there any questions or issues?
This would obviously be different for other countries, right?
Yes, very different for other countries. Okay, so this is for the United States, where we are predominantly European, and so our data values are similar to Europe. Europe is generally a little bit taller. Other parts of the world, like Asia, generally a little shorter. Anyway, there's a long article, or not article, but just page of just these values on Wikipedia. You look up human height by country, they have it. They don't have the standard deviation numbers though. You have to go to like health agencies to get that. And it's around 3, it's not exactly that, okay? What if I asked, what if I didn't choose one of these nice little numbers here, okay? What if I didn't say what percentage of women have heights lower than 61.5, but I said what percentage of women have heights lower than 62 inches? What do we do then? Okay, so let's just put this up on the screen. So we are not dealing with cholesterol, but okay, so we said the mean height is 64.5 and the standard deviation is 3, and again an approximation, so we're at, so if I didn't ask 61.5, but I said what percentage of women in the US, and I should say adult women, have heights lower than 62 inches, okay? This question is now difficult to answer with the tools that we have, or actually it's not possible to answer with the tools that we have, okay? So 62 would be somewhere like right here, okay? So here I'm drawing a line at 62, and I want to know essentially how much is shaded over here. Let's use a slightly Okay, well, to answer this, this is where we have reference tables, okay? We have reference tables that will help us get all of these things, okay? Except the reference tables, in order to be versatile for all the possible normal distributions, because I said all normal distributions have the same shape, it's just, we just change the mean and the standard deviation. To be versatile, the reference table uses a mean of 0 and a standard deviation of 1. Okay, so we have reference tables. And the table is known as the standard normal table. And uses mu equal to 0 and standard deviation equal to 1. Okay? It's also known as the z-table. So essentially, we want to convert all of these numbers so that they have a mean of 0 and a standard deviation of 1. Okay? And this is known as a z-transformation, or just basically finding the z-score. Okay? And so a z-score is the number of standard deviations, or the distance from the mean expressed in standard deviations. Okay? So a point of 64.5, that value, so using this here, if y is equal to 64.5, that has a z-score of what? 0, okay? Because the distance from the mean is 0. 64.5 is the mean, so its z-score is 0. If y is equal to 61.5, its z-score is -1, okay? Because each standard deviation is 3. 61.5 is 1 standard deviation below the mean. Its z-score is -1. If I go all the way up to 70.5, y equals 70.5, that has a z-score of what? 2, okay? So what is the z-score of this point at 62? Yeah, what is the z-score of y equal to 62? Okay, well, we know it's going to be between 0 and -1. Can we express this distance from the mean in standard deviations? Sure. We're just going to take the distance from the mean. So how far is 62 from 64.5? It's 2.5 below. So I would just do 62 minus 64.5. And I get -2.5. But I want this expressed in standard deviations. Each standard deviation is 3 inches, so I'm going to divide that by 3. And so -2.5 over 3 gives me -0.83333. Okay, so this z-score is -0.8333. Okay, and so all I did here to get my z-score is I took the value y, I subtracted off the mean, and I divided that distance by the size of the standard deviation. Okay, so maybe that's a useful formula. Z is equal to y minus the mean divided by the standard deviation. Okay, and that relates directly to our definition of a z-score, which is the distance from the mean, which is y minus the mean, expressed in standard deviations, we just take that distance, divide by sigma. Okay? So we have, okay, we still haven't answered our question, right? What percentage of women in the US have heights lower than 62 inches? Okay, so all we've done is we've successfully turned 62 into a z-score of negative 0.8333. Okay, so let's copy this. Okay, so we have, actually, let me copy this top part. This is the question we're still going after. Sorry. Okay, so we have z is equal to negative 0.833. Okay, so if you go into your textbook, I think in the inside front cover of the 5th edition, or and also just in the reference section, where are they? I have no reference tables in my, are there no reference tables in this textbook? The new one, the 5th edition. Is there no section for reference tables? Where are they? Statistical tables, page 636.
Well, the first page has them.
Oh man. Selected chapter appendices can be found on pearsonhighered.com. What? Okay. Well, all right. Let me pause this video. I printed out reference tables for all of you. Okay. But I'm surprised that they took them out of the 5th edition. That seems. Huh? They're in the 4th edition in the back of the book, but apparently not worth printing in the 5th edition. I don't know. Okay, well, I've got them here. I'm going to pass them out for you guys.
I think it was the same with the binomial coefficient.
Okay, so I'm hoping everybody got their tables. And these tables are for you to keep. Please don't lose them, and bring them to class each week. There will be a few quizzes where you will use these tables, and you will want to make sure you have them. Okay, if you forget your tables, I'm going to have to say I'm sorry. Do your best without the tables. Okay, so make sure you bring them. If you want to take off the staple and put them in, sheet protectors or whatever you want to do, that's up to you. Okay, and apparently if you lose them, you can go to pearsonhighered.com/mathstatsresources. I guess I'll put a link to that, so you can always go there and print off your own copies. But anyway, the first one is the normal table, and we will go over using it, and the other tables we'll discuss as the time is appropriate. Okay, so let me open up this table. All right, so table 3 is areas under the normal curve. And you can imagine let me just move this down. No, I don't want that. Okay, changed my mind. You can imagine if I were to draw a normal curve here. So I'm going to draw the ugly one with my own drawing skills here. So if I draw a normal curve here, and I have z equal to 0, and I shade in everything over here, I guess I can use this. How much would I have shaded in if my picture were good? this should be 50%, right? And so if we go to our normal table, okay, remember z is equal, here z is equal to 0.00, okay? And so this would actually be on the second page of the normal table, and you can look in the top left corner, 0.00, this intersection is 0.50000, okay, or 3 zeros. So 50%. Z is equal to 0.00. Now, this table represents numbers in a slightly, not odd, but just in a different way, okay? So, Z equal to 0 is essentially 0.00, and you find that by going in the table to the row 0.0 and the column 0.00, and that's how we get 0.5000. Now if I go over 1/100th to the right, I go, let's change colors here. If I go over here and I shade this in, so I just have a tiny bit more, okay, tiny bit more shaded, just that tiny little, add that tiny little green sliver, and I'm using z equal to 0.01, so I've gone over just 1/100th of a unit. The amount shaded in, I would have to go to, I would still be in the row 0.0, and I would go to the column 0.01, and I believe the amount there is 0.5040. Okay, so if I just add a tiny little sliver, 1/100th of a unit big, the amount I have shaded in is to the left is now 0.5040. Is that okay? All right, and so we, you have to just get used to representing numbers as up to the 100th place by looking up a row and a column. So if you had z equal to 1.36, you would go to the row 1.3, the column 0.06, and at that intersection in the table, 1.3 and the column 0.06 gives us 0.9131. Is that okay with everyone? Okay, so that's, you know, it's a normal distribution and it's continuous, so there's technically infinite number of values that z or y or whatever can take on. And so when we're looking at our problem here with a woman who is 62 inches tall, her z-score is negative 0.83. Okay, we're going to have to round off to 2 decimal places to look that value up in the table. And so we would look up z equal to negative 0.83, and the table tells us that the amount shaded to the left is how much? So negative 0.83 gives me 0.2033. So the amount shaded, so from the table we have 0.2033. Is that okay? Okay, so that would be the answer to our question. What percentage of women in the US have heights lower than 62 inches? Our answer would be 20.33%. And of course, we wouldn't expect it to be exactly this, because the normal distribution is an approximation anyway to the actual height data. But the normal distribution says that 0.2033 have z-scores lower than negative 0.83. Okay. Yes?
Are there negative and positive 0 because it's a limit?
No, it's just the design of the table. Okay. The table goes to negative 3.49 and positive 3.49, and at that you have 0.0002. And essentially, if you go beyond, or 0.9998, if you go beyond that, you can just say close to 0 or close to 1. Okay. One thing to keep in mind is the table always gives the area to the left. Okay, always. So if I were to ask almost the same question, but instead I said, what percentage of women have heights taller than 62 inches? You would tell me what? Yeah, you would just do 100% minus 20.33, right? So if I said, what percentage of women have heights taller than 62 inches? You would do 1 minus 0.2033, and you would get 0.7967, and you would tell me 79.67%. Is that good? I want to copy this thing again because it's very useful. Okay, so we can let's just do a couple practice drills just to check our understanding. I'm going to do a bunch of these.
Wait, just real quick.
Yes.
Instead of subtracting from 1, would it also be possible to flip the sign?
Yes, yes. So you could also, that's very good because it's symmetric. You could look up negative 0.833 or negative 0.83, get 20.2033, and do 1 minus that. Or you could look up positive 0.83, and the area to the left of positive 0.83 would be the same as the area to the right of negative 0.83. Okay. If that made sense, great. If it did not make sense, don't worry about it. You can always look up the z, find the area, subtract the area from 1, okay, and get the area to the right. I think we'll try a few practice drills, and I think we'll get maybe the hang of some of this stuff here. Okay. All right. So I'm going to just do several of these. Okay, so I'm going to say here, we're going to say the mean is 115. No, we'll just say 100. Standard deviation is 15. And I'm going to ask what percent have scores, what percent is higher than 122. Okay, and over here I will say mu is 17, standard deviation is 2.4. What percent is lower than 20.6? try those two out first, and then we'll do one more together. So I'll give you guys a couple minutes to figure these out. How are we doing? Okay, I'm gonna go ahead and start working through some of these. All right, so this first one over here, our mean is 100, and we're asking what percentage is higher than 122. So, you know, these tick marks are here. You don't have to worry about drawing tick marks if you don't want to, okay? The important thing is just that you put 122 to the right of 100. That's the only important part, okay? And if we want to shade in something, we're shading the area to the right. Okay, so this is what our picture looks like, and we just want to know what is this area right here. Okay, so we're going to use our table, so that requires that we turn this into a z-score, so we're going to go 122 minus 100 over 15, and we see that we are 1.4666 units away, or standard deviations away from the mean. Okay, when we go to our table, we have to round off, or actually I guess it would be 7. We have to round off to 2 decimals. So we're going to round off to 1.47. Okay. Now, again, we can look up 1.47, and if we do that, we get 0.9292, but that is always the area to the left. So the table tells us that the area over here is 0.9292, and so the area to the right over here is going to be 1 minus 0.9292. Okay, and so our answer would be 0.0708, or as a percentage, 7.08%. Okay. Alternatively, if you want to just look up negative 1.47 and find the area to the left of negative 1.47 because it's symmetric, you would get 0.0708. Same deal going on over here. 17 goes in the middle because that's our mean, mu. Our standard deviation is 2.4, and we're asking what percentage is lower than 20.6, okay? You don't have to worry about the tick marks. The only important thing is that 20.6 is to the right of 17, and we're asking the area to the left, okay? We just want to know how much is shaded over here, okay? So we turn this into a z-score. 20.6 minus 17 divided by 2.4. We get a z-score of positive 1.5. We look that up in the table. Look up z equal to 1.5 in the table. The table gives us the area to the left, which is what we want, and we get our answer is 0.9332. Is that okay? All right, why don't we